And so this is the title of my presentation that links in, of course, with your current studio project about environmental resilience. And I had a look at your project handout, and I noted that there are basically 3 questions that your design projects have to answer. And so obviously your task as students is to provide an architectural response to each of these questions. How can architecture survive against the current natural and environmental conditions? Secondly, how to use the potential of nature in an architectural configuration. And the third question for you to reflect on in this project is, are there any innovations that can be applied to the architecture? And so as I go through this lecture, I will be addressing some of these questions sort of directly and indirectly. I suppose I could just make a comment about the first question. How can architecture survive against environmental conditions? Well, when it comes to earthquakes, which is probably one of the most severe environmental conditions that you face, then your architecture can survive if you design the structure to be adequate for the earthquake forces that will occur. And so in the lecture today, I'm going to be giving you basically the principles that you need to apply to your building to make sure that it can survive, you know, an earthquake that is very likely to occur at your site. And so I'm going to begin and concentrate pretty much in this lecture on earthquake load resisting structure. And you are going to have to design such structure for your design project. You're not going to design it in detail, but you can design it conceptually so that it can be seen on your plans and sections. But as you provide this earthquake resistant structure, it's very important that it follows 2 criteria. First of all, any structure that you provide in your design, it must integrate with your program, the use of your building. And so every column and beam that you design, you know, should integrate with the use of the building, and it shouldn't hinder it. Ideally, it should enhance the program and the way people use your building. And secondly, when it comes to designing the structure of your building, please ensure that the structure you provide enhances your design concept. So you've got to keep reflecting on your design concept as you think about your structure. For example, if your design concept is about, expressing the strength of your architecture to resist a natural catastrophe, then you will want your structural elements probably to be large and to be visible. If, on the other hand, your concept is about perhaps transparency or lightness, then you will perhaps want to hide your structural members and just emphasize transparency through glazing and so on. But further, as you reflect on your design concept, there should be some aspect where it connects with the theme of environmental resilience. And so when you are doing your design, hopefully the structure you provide to resist earthquake is going to enhance your design concept, and in particular, speak to the issue of environmental resilience. So those are just two aspects of structural design to keep in mind in your particular design. Now, when we think about the need to design for earthquake, I turn to this map of Indonesia, which shows the earthquakes that have occurred in the past approximately 120 years. And you can see that your country is a very, very seismically active area. It's really only Kalimantan that is pretty much devoid of earthquake. But certainly all the other islands of Indonesia are very prone to strong shaking. And so as an architect, you have to assume that one day in the life of your buildings, they will experience really strong and violent shaking as the ground moves under them. And so whether your site is in Surabaya or Bali or Padang, you must design for earthquake forces, which are far more serious than other forces that your building must withstand. And so I'm going to begin by talking about, I'm just having trouble seeing my screen here. Just excuse me. I'm talking about the use of vertical elements or the structural layout that you will require to resist earthquake. The configuration, the layout of the vertical elements that you will show in your plans and your sections. Now, the first principle of earthquake resistant design is that as architects, we must provide resistance in both orthogonal directions. And so we need to look at this graph at the top of the screen. I just want to make sure you can see my mouse. Can you see the mouse?
Yes, yes, you can see it. Yes.
And so here I show the x-axis and the y-axis. Now I want you to imagine that your building is somewhere at the center of these two axes. And so imagine that your building is a little dot just here. Now, during an earthquake, the ground will shake in every direction. 1 second, the ground might be shaking in the y direction. The next second, it might be shaking in the x direction. The next second, it might be shaking in this direction or this direction. Our buildings get shaken randomly. And so we have to have a strategy of making sure that no matter the direction of shaking, our building is safe. And so it is quite simple actually, because if, for example, we have shaking at an angle of theta to the x-axis, this shaking will cause forces of this amount in the x-axis and this amount in the y-axis. And so we can resist this shaking by providing strength in the x direction and strength in the y direction. And so if we have sufficient strength in the x direction and the y direction, then your design can withstand shaking from any direction. This is the first principle. And so an example of it is here. Here's a very simple building plan with 4 structural walls resisting earthquake. In the x direction, the earthquake forces are primarily resisted by this structural wall and this structural wall. These 2 walls are not strong in the x direction, and these columns are quite weak because they're so small and flexible. In the y direction, this wall and this wall will resist the earthquake force. And so with this particular layout, we can make sure that our building is strong in both directions. And so when it comes to your building, you can superimpose on your building plan an x-axis and a y-axis, and then make sure you have strength in those 2 directions. And then you are applying the first principle of earthquake-safe design. Now I'm going to talk about the different structures that you can use to resist earthquake. And I want to begin by making a few words about post and beam structures and structural walls, because those 2 structural systems are very common actually in every country in the world, but they are not good at resisting earthquake. Let's look at a post and beam structure. By definition, a post and beam structure consists of posts with pins or flexible joints at the bottom and the top of each post. And the beam is just like simply supported, resting on top of the posts. Now, this structure is very stable under gravity load, under vertical load. It's very good, very suitable. However, if there is any horizontal load acting, a post and beam structure becomes a mechanism and it will just fall over. What about walls? A load-bearing wall is very good for gravity loads. I mean, it acts like a massive column. But if there are loads in this direction on a wall, it will just fall over. And so it needs support for forces in this direction. We call them out of plane loads or forces. Of course, this same wall, it is actually quite strong in this direction. And so this wall is able to resist forces in this direction, but not in the other direction. In the other direction, it's dangerous. So the next principle of earthquake-safe buildings is that you as a designer have to choose one of these three structural systems for each of your directions and plan in your building. So you have to choose, and you make your choice based on your program and your design idea. Okay, that's what should govern your choice of structural system. Once you leave the School of Architecture, you will also make that choice based on cost. But while we're in a School of Architecture, we're not expected to worry too much about cost, are we? We are concerned about program and architectural idea. And so in your building, you must choose one of these systems in each direction. For example, in one direction, you could have shear walls resisting earthquake forces. In the other direction, you could also have shear walls, or you could have braced frames, or you could have moment frames. The choice is entirely yours. And of course, once you've made a choice of one system, you must stick with that. But you can have as many elements as you want to. And I'll come to this later. If you want to, you could have moment frames in one direction and braced frames in the other. Or you could have moment frames in both directions. But you have to make the choice and show the structure in your drawings. Let me say a few words about shear walls. They are the best system for resisting earthquake forces. They have by far the best track record of surviving earthquakes. The best shear walls are made from reinforced concrete. Then they can be made of reinforced masonry. And in Indonesia, for your many houses and low-rise buildings, you might use what we say are confined masonry walls to resist earthquake forces, just for low-rise construction. But in your current project, which is between 5 and 10 stories, if you use shear walls, you would definitely use reinforced concrete shear walls. And these shear walls, they must start at the foundation on top of a foundation beam, and they must go directly from there to the roof level. They've got to be continuous up the height of your building. So you've got to find areas in your plan where these walls can pass the entire height of your building. In other countries like in the US and New Zealand, we sometimes use plywood shear walls or shear walls from CLT. CLT, in other words, engineered timber products can also create shear walls. And so here is a typical shear wall. It requires usually a deep foundation beam, and often it will have tension piles underneath the beam. And the wall will be continuous right up to the roof, and it will connect at each floor level. If you require fairly large penetrations in a shear wall, the shear wall is called a coupled shear wall because we require these special beams that couple these two parts of the wall together. But wherever possible, you know, try and avoid large penetrations in a shear wall. The next type of system is a braced frame. And braced frames work through triangulation. You know, if you have members that are triangulated, that creates a strong structure. And so when it comes to braced frames, you architects can choose the type of frames you want. You could have a cross-braced frame, or an inverted V-braced frame, or whatever. The choice is yours. And once again, you make that choice based on your program and design concept. There's one special type of braced frame that is unusual. It's called eccentric bracing. And you'll notice that the triangles here are not perfect. They're not triangles actually, because we have this eccentricity between the tops of the braces. And this creates a structural fuse region. So this type of bracing is the most ductile. It's able to absorb earthquake energy without breaking. And it's probably the most economic form of cross bracing. The beams must be in structural steel, but in all these other braces, it's possible to use reinforced concrete as the bracing members. The final system that you can choose is that of moment frames. And here's a little building that is resisting gravity and earthquake loads using moment frames. A moment frame consists of three elements really: columns, beams, and rigid joints. In other words, very strong joints between the columns and the beams. And it's those joints that give these frameworks their strength and rigidity. So these are moment frames. And these are the most flexible of the structural systems on offer. They're probably the most sensitive to construction error, and therefore they're not the most recommended, but as you will be aware, they are used very, very widely in Indonesia and throughout the rest of the world. And you are free to use these frames in your design. This is what a plan of a moment frame looks like in reinforced concrete. There's the beam dotted in, and see the two columns? And notice the way the columns are orientated. The columns must be strong in the direction of the frame. Like this is wrong. Here's the beam, and see the columns are orientated the wrong way. And so when we have a moment frame, it's really important that the columns are orientated so that they are strong in the direction of the frame. Otherwise, the frame will be very flexible and weak and maybe dangerous. The same principle applies if we're using steel construction. This is a steel moment resisting frame. Steel beam, steel columns. And see the columns are strong in this direction, but it would be a mistake to create a moment resisting frame like this, because the columns are weak for bending in this direction. So this is wrong, this is correct. So if we look at a very simple one bay single story frame in elevation, it looks like this. This is the column, this is the column depth, this is the beam resisting the roof slab and resisting the earthquake forces, and this is the rigid beam column joint. And this would be a section through the beam. The beam depth would be considered the depth of the beam plus the topping of the floor slab. That would be the overall depth that you would provide in your design. So when it comes to moment frames and even braced frames, you can have as many frames and bays in your frame as you want. You decide. And once again, your decision is based on your design concept and your program. You won't have very few frames, because that would mean that your structural members would be too large, and that would probably be inappropriate for your designs. So you have to create a balance between the numbers of frames and bays and the sizes of the members. You know, the more frames and bays, the smaller the members. But you're able to make that choice for your concept and program. Now, the next principle of seismic design is that in each direction, you must separate parallel systems in plan, and you must provide a minimum of 2 structures in each direction. Okay, so in each direction of your building, you must have at least 2 moment frames or shear walls or braced frames. And those 2 frames or walls, they must be separated in plan to give the building its torsional resistance. You see, during an earthquake, a building will twist in plan. And so we must separate our frames so that they are able to help resist any twisting that will occur during the earthquake. I want to just show you a couple of examples. These are designs that I designed using the Resist software that we'll come to later. But in the left-hand building here, the earthquake forces, this is the Y in the Y direction, they are resisted by 2 moment frames like this. 1, 2, 3, 4 bays, 2 frames with 4 bays. You can see the frame on this side of the building, and you can see the frame on the other side over there. Now, what about in the X direction? In the X direction, these frames are useless because they're not strong in the X direction. They're only strong in the direction of the beams. So in the X direction for my building, and I think you will agree with me, this is a very boring building, isn't it? But it's illustrating my principle here. In the X direction, I've designed 2 shear walls at each end of the building. One shear wall here, the other shear wall here. And those shear walls are widely separated to give very good torsional resistance. If we wanted to, we could bring these shear walls into the plan of the building if we wanted to, and that would be fine. So this is one design of my building. Then I did another design, and what I did was I said that I just wanted two bay frames. And so now I've made a 2-bay frame here in the Y direction and another 2-bay frame on the other side of the building, but not exactly opposite the original frame. But I mean, both of these frames are strong in the Y direction. And because there are only 2 bays, these members are going to be a bit bigger than these members. Okay, the cross-sectional areas here will be larger than these members. And so as an architect, you have an infinite number of options to resist earthquake. Please note that I haven't shown columns here that you would need for gravity resistance. I'm just showing the structure you need to resist earthquake, because it's a lot larger than the structure to resist gravity. Like here, we would provide columns, but they could be quite slender, you know, probably about half the size of these columns. So, I mean, this design would be great if you wanted this end of your building to be very transparent, for example. Now, I've told you that you need structure. I've told you that you need at least 2 lines of structure in each direction, but you could have a lot more lines if you wanted. And so I imagine that the question in your minds is something like this: how much structure do I need for my project? Like in your mind, maybe you've already got your plans, you've done a preliminary sketching, and you roughly know the size and shape of your building. Well, how much structure do you personally need for your building? And so that's why we have developed the software Resist, and I believe most of you have downloaded it, and I'm going to give you a demonstration in the second half of this lecture today. But if you haven't got access to Resist, then for you to know how much structure to use in your design is very difficult. And so what I would recommend to you is that if you've got no other options, then you should go to perhaps Ching's book. I think the title is Structure Illustrated. Or you could go to Precedents. You could look at a building rather similar to yours in size and height in Surabaya, and base your structural dimensions on that building. And finally, you should get advice from your tutor. Your tutor should be able to give you some idea as to what the size of structure you need to resist earthquake. But by far the best way is to use the software called Resist. Now, so far in the lecture, I've talked about vertical structure to provide earthquake resistance. And it's the vertical structure, the beams, and particularly the columns, but also the beams and the shear walls. They are the elements that do most of the hard work during an earthquake. However, we also have to pay attention to horizontal elements in our buildings. And if we look at this building here, it's a very simple building and plan. I've exaggerated the columns forming a moment frame here and here in the X direction. And in the Y direction, we've got two structural walls. If we look at a cross section through this building during an earthquake, we can draw the earthquake inertia forces that act wherever there is mass in the building. Now, most of the inertia forces occur within the floor slabs because they are relatively very heavy. However, there will be other inertia forces from the weights of the columns and infill walls and partition walls, etc. And so in an earthquake, all these forces are acting like this on this story. If we look at these forces in plan, they look like this. Here's the length of the building, here's its width. And so over every square meter of the floor slab, there is an inertia force. Now, all these inertia forces have to be resisted by the two shear walls, one at each end. And so the job of the floor slab is to function as a horizontal beam. We call it a floor diaphragm. To transfer the inertia forces from the middle of the floor slab to the safety of the shear walls. And so in your building that you are designing, the role of your floor slabs is to transfer the forces into your moment frames or shear walls. Your floor slabs also have to tie your building together so that during an earthquake, it doesn't sort of fall apart. And so your floor diaphragms are really important. And so if we look at a typical floor diaphragm, here are the inertia forces acting. We can do like a mathematical model. And here are the inertia forces, and the supports are the shear walls. So essentially a diaphragm is a beam. It's a horizontal beam. It just works horizontally. I mean, most beams work vertically, but during an earthquake, your floor slabs and roof slab have got to create a horizontal beam action. And like any beam, it has a deflected shape, it has shear forces in it, and it has bending moments like this. And for your roof, even if you've got a light roof, you must create a diaphragm using horizontal trusses to transfer the inertia forces to the bracing, wherever it is in plan. In this building, the bracing is at each end of the plan. Now, because your floor and roof slabs function as these horizontal beams, you've got to be very careful about penetrations. Because, you know, if you put big notches in your floor slabs, that's going to destroy the ability of your floor slab to span horizontally between your shear walls or your moment frames. And so this would create a very dangerous design. However, if you had the beam running through here, this would be okay. This is the best place for a penetration in the middle of a floor slab. But this is a dangerous place here because during an earthquake, the forces want to be resisted by the structural wall. But because this is a void, a penetration, then the floor slab is very weak here and here, and it will probably break and cause very severe damage in your building. So you have to be very careful about where your penetrations are. You know, have you got an atrium in your building? Be careful. Have you got large elevators or stairs? Be careful where that penetration is. You can have these penetrations as long as your floor slab is strong enough to tie everything together. No problem. What about re-entrant corners? Some of you may have configurations with re-entrant corners, like here, 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 and here, here, and here. Re-entrant corners are very popular among architects, but in earthquake regions, they cause all sorts of problems. Because in plan, if you have a re-entrant corner, the two wings of the building have different dynamic characteristics. And so for shaking in this direction, this wing will move a lot further than this wing. And so these are areas, this is the area of damage to your floor slabs. And so as architects, we avoid re-entrant corners by designing seismic separation gaps. If we have a building H-shaped in plan, what we will do is to create a physical gap here and here and design our building as three independent structures. Each structure looking after its part of the building. And so this part of the building, it must have resistance in this direction and this direction. This part must have resistance in the X direction and the Y direction, and so on. And so this gap, it has to be a pure gap covered with flashings and treated architecturally. And it has to be large enough so that during an earthquake, these different structures don't hit each other, don't pound each other during the shaking. And there's information about this in my book, Seismic Design for Architects. So I'm going to have a break now and just invite a period of questions and comments from you, and then we'll move on and I will give you a demonstration of the Resist software. I believe is that right, Ibi Fenty?
Yes, that is right, Andrew.
Okay.
Yeah.
Well, perhaps you could see if there are any questions or comments. And it's fine if the students ask them Bahasa Indonesia, and you can translate them for me if I don't understand them.
Ya, oke. Ya adik-adik, ini waktunya tanya jawab. Silahkan kalau ada pertanyaan raise hand atau ditulis di chat box. If you cannot use English or you're not confident with your English, then you can write it in bahasa, and then I will try to translate it for Andrew if he doesn't understand. Jadi Andrew ini sudah sering ini ya ke Indonesia, jadi I think he is rich with vocabulary in Indonesia, so sometimes he can answer it directly, but yeah, you can use English instead of bahasa first. Silakan apabila ada pertanyaan, raise hand atau ditulis di chat box. Oke, ada Gaby. Silakan Gaby.
Ya, saya tanya pakai bahasa Indonesia aja ya, Bu. Jadi,
Oke.
yang dijelasin itu kayak apa ya, mempertahankan posisinya dengan beam and columns yang mostly itu dari concrete sama steel. Kind of. Kalau saya mau menggunakan struktur yang apa ya, saya nggak mau pakai kolom, nggak mau pakai baja, mau pakai kayu agar lebih resilient. Apakah itu memungkinkan dengan prinsip-prinsip yang kayak tadi?
Oke, terima kasih Gaby. I think, okay.
Can I just summarize that question? So are you asking about the materials of construction?
Yes, exactly.
Okay, well, the answer is, if you want to use moment frames to resist earthquake, the frames can be, your columns and beams can be in reinforced concrete, your columns and beams can be in structural steel, or your columns and beams can be in wood. But if you are using wood structure, you would want to have your floor structure also out of wood to keep it lightweight. But you certainly can use any of these structural materials if you want to. Is that answering the question?
Gimana, Gaby?
Ya, agak mudeng-mudeng.
Oh yeah.
Thank you so much.
Okay, so I think yeah, it answers the question. But there is one thing that Gaby also asked, whether those systems that you have explained can be applied for other materials as well. So is it okay for using those those rule of thumbs into another material?
Yes, the same, all the principles that I've given you apply to any structural material. And also the principles I've given you also apply really to any height of building. So you can be confident that, yeah, no matter what the material or the height of building, if you use those structural principles, you would have really good earthquake-safe construction.
Okay. Okay, thank you, Andrew. Thank you, Gaby. And then next we have Miranda. You can ask your question, Miranda.
Saya juga nanya pakai bahasa Indonesia aja ya, Bang. Kalau bisa.
Okay, yeah.
I want, Mr. Andrew, I want to ask about the seismic separation gap, how it works. I don't really understand about how it works.
Okay, well, let me share with you a whiteboard. And please excuse my bad drawing, but here are two buildings. Separated by a seismic separation gap. And so if we draw a section through the buildings, we've got one building and it's got columns and beams. And here is the second building. And there is a gap. Oh, this is the beam. The beams. And this is the gap here. This is the gap. And what happens is that, like this is the floor slab. The floor slabs, they stop at the edge of the gap. And here we have a sliding plate. A plate that allows sliding when the buildings move out of phase. And the width of this gap, it depends on the height of the building and on the flexibility of the building. And so you've got to ask your structural engineer what the width of that gap must be. Like for buildings that are, say, 5 stories high, the width of this gap, it might be in the order of, say, 30 centimeters. That will be the approximate width of the gap. For a 10-story building, we might need a 60 centimeter gap between the buildings, but it depends on the height of the building and the flexibility. And really you have to look at one of the pages of my book to get more information about that, because it's sort of rather complicated. Does that answer your question?
So the building seems like menyatu, unite in one kesatuan apa ya, Bu?
United. Yaudah,
But
kamu bangsa dulu. Ngomongin aja dulu satu kalimat.
Bangunannya itu berarti jadi satu kesatuan tapi mempunyai struktur terpisah.
Correct.
Yeah.
One design, one work of architecture, but 2 separated structures.
Okay. Thank you, sir.
Andrew, is it different with dilatation?
Yes, it is. A dilatation is really a separation gap to control shrinkage and temperature expansion. And those movements are usually quite small compared with the movements that occur during an earthquake. So a dilatasi it's the same principle, but the width is generally a lot narrower. That's a very good question. These are very good questions.
Okay, thank you.
Okay. Next. Gaby, you want to ask another question? Oh no.
No.
I'm curious with the plate, the material of the plate, Bu Fenty.
Yeah, me too.
Is it baja atau apa?
Can we use steel or something, and how it because if it is like only sit on top of it, so how can we stick it into the plate? I mean the floor plate from one building to another building. If this one is like this is, it feels like it sits on only on top of the structure, but how can it sticks to the structure itself?
Yeah, it's baja. It's always steel. We fix it here. We fix it at this end, and this end, it can slide. So this is the top of your floor surface.
Mhm.
Top of the floor surface.
Mhm.
This is your steel plate.
Mhm.
Can slide.
Oh,
So it just slides like that.
right.
So here there are some screws.
Mhm.
Maybe here just one really small screw that will break in an earthquake and allow the plate to slide.
Oh, right. Okay.
I've got some photographs of this in my book.
Yeah. Okay. Thank you, Andrew. Next question. Bagus Guna. Silakan.
Ya, mau nanya, kalau tadi kan kebanyakan contoh bangunannya itu yang rigidnya berbentuk apa namanya persegi panjang begitu. Kalau bangunannya berbentuk sirkular gitu bagaimana Bu ya? Jadi antara kolom yang antara sisi sebelah kanan dan kiri itu beda panjang dari bangunannya gitu.
Yeah. So he's asking about a circular form of building.
Well, you can draw your axes in anywhere. And so we need strength in the Y direction, maybe 2 shear walls. And in the X direction, maybe some moment frames. So it's exactly the same principles. These principles I've given you, they will apply to any shape of building, whether it's circular or any shape that you can think about that excites you.
Kalau di tengah-tengahnya itu seandainya bolong begitu, gimana ya kira-kira? Jadi nggak nyambung antara sisi semuanya.
Maksudnya di tengah ada void atau gimana nih, Bagus Guna?
Jadi bentuknya kalau boleh saya annotate, izin Bu.
Okay. He would like to draw what he think about his building. Is it okay, Andrew?
Yeah, as long as it's very fast.
Okay.
Yeah, okay. Bentar. Kamu mau share screen ya? Wait. Udah. Sudah? Bagus, silahkan share screen, terus whiteboard dipilih.
Jadi di sini dia nggak nyambung begitu. Bangunannya di bagian sininya kosong. Di bagian yang saya berikan garis itu kosong, sir.
Okay, so this part is, well, I think this part, wait, where's my pen? Okay, this one is having no floors, Andrew. So the building is only this. It's like 2/3 of the circle. I think it's the same using X and Y. You can find it. Sorry, my drawing is so bad using this device.
Yes, it's horrible, isn't it, drawing with a mouse?
Yeah. Okay, Andrew. This is what he means about a circular building.
Yeah. Well, look, this is okay. You just need to draw your axes and provide strength, on both of those axes.
Ya, bagus. Jadi sama aja dikasih X sama Y gitu. Habis itu nanti yang merespon X mana, yang merespon Y mana gitu. Untuk sisi-sisinya ini juga dianggap ya. Jadi tidak hanya sisi yang lagi-lagi ini ngomongin tentang sisi terluarnya. Jadi mungkin yang ini juga nanti dia merespon X atau Y-nya gitu. Jadi kan dindingnya kan ini kan ya yang terluar ya jadinya.
Iya,
Bagus. Nah, itu. Jadi sama cari X sama Y-nya karena ini kan nanti side based ya. Kalian kan bisa mana yang utara, mana yang selatan. Nah, itu terserah kalian gitu. Jadi itu nanti tetap pakai prinsipal harus pakai yang X Y itu terus nanti merespon yang mana dulu seperti itu.
oh iya. Makasih Bu.
Oke.
Makasih Sir.
Okay. Now we have a lot of questions.
Look, we haven't got time. Maybe we've only got time for 2 more questions.
Okay, 2 more questions. Then we have Anastasia.
Yes, thank you. I actually have 2 questions in mind. One is because you said that by the principles that you share just now, it is ideal to use like spreaded columns and what I thought in mind, what if we want to use like one big centered column that the building can depend on? Is it ideal for the situation in Indonesia where it is very prone to earthquakes? And the second question is actually,
Look, can I answer your first question?
oh yes, sure.
The answer is yes, but if you have a building, you are able to resist all the earthquake forces if you have like a central structural core. But your core must be quite large in plan. But certainly, you can have say a square, or you can have a building of any shape, and if you have a strong structural core, then that will function as you say, like a strong column that is able to resist the earthquake forces, you know, in both directions. So yes, you can have a central core. So now what about your second question?
My second question is actually about my design, where there is an existing building that I want to apply to my current design. What kind of structure that is suitable to adapt to existing buildings as such?
Well, it sort of depends if your existing building is safe or not. If your existing building is not safe for an earthquake, then you've got to retrofit it. Like, you might have to add additional new structure into it to make it safe and reliable for earthquake. And in many countries, you know, retrofitting for earthquake forces is very common. In my own country, for example, you know, many buildings are being retrofitted. They were discovered to be unsafe, and now architects and engineers have perhaps put in some new shear walls or some new moment frames. These have been inserted into the building to make it safe. So what I would suggest you do is if you Google, you know, seismic retrofit, then you will get some quite useful information about how to treat existing buildings. I mean, there's a chapter in my book as well that would give you information. Okay, so we have one last question.
Thank you, sir.
Okay, thank you, Andrew. I would like to highlight what Andrew means by retrofit. Kalian tahu nggak kata-kata retrofit? Ini ada yang geleng-geleng nih. Nggak ya? Okay, so retrofit, it's like retrofit itu kayak pembaharuan atau pemugaran kembali atau penyegaran kembali sebuah bangunan. Jadi ada bangunan lama, kemudian di upgrade itu diperbaiki fungsinya, strukturnya ataupun apapun yang terjadi damage di situ untuk sesuai dengan masa sekarang. Namanya retrofit itu, namanya retrofit. Jadi if you try to find the translation in Bahasa, I don't think you can find it, but it is a common term for us to use when we have like historical buildings or buildings that need to be preserved, but we have to enhance the performance of the building. Jadi itu retrofit, tulisannya ya retrofit biasa gitu.
Bukan meretro bangunan 70-an ya, Bu ya?
Bukan Pak. Okay, that's so the last question maybe from Makfiro Robania. Oh, I think the other question could be written in the chat box, and then in the meantime, if we have more time or we have some time, spare time, then Andrew can answer it. Okay, Andrew. Makfi, silakan.
Yes, Miss Fenty. I want to ask about the configuration of horizontal elements that I really understand about that because that I know it's like a diaphragma system. It's like distribute a force to the column, and actually how it works, how the applicant the diaphragma system in our building. When I'm looking for in internet, it's like a beam that are made in a rigid on the floor slab. It is true or not?
It's partially true. The strength of a floor diaphragm, it comes from the thickness of the concrete of your floor slab. So when you are resisting horizontal forces, the beams are not very important. What is more important is just the area of concrete flooring that will create your strong horizontal beam for you to distribute the forces to your vertical elements. Do you want to ask me like a secondary question, or is that clear enough?
It is true that we should make a small beam in the horizontal plane. It's like not a main structure beam. I mean.
Yeah, no, you don't need any small beams in the horizontal plane. You just need your floor slab that will do the job.
Mm.
So the only beams you need in your design are to resist the gravity loads.
Yeah.
Or beams that are part of a moment frame to resist earthquake forces.
Okay. It's answered my question. Thank you, sir.
Thank you. Nice question.
Okay. I think you can continue, Andrew. Yeah.
Okay, so I'm going to continue by just showing you how to use this resist software. So this software is a rule of thumb software. Okay, it's just for approximate sizing of the structural members to resist earthquake. And so there's no need to be too accurate. this is, as I say, it is rule of thumb software. And in the help information, there is a step-by-step tutorial and other information about the software. There's also a YouTube video, a video on YouTube of me explaining how to use this software. But just briefly, what we do is we move along these tabs at the bottom. So we start off at the building tab. What type of building have you got? I mean, if you've got, I think you're designing a commercial building.
Yes.
Correct?
Yes.
Righto. So you will have a normal structure. You won't be designing like for a hospital with post-disaster functions. You will be having a normal structure. Number of stories. I believe your building is between 5 and 10 stories high. So say 7 stories high. The average story height, the roof height, the weight of the floors. That's a lightweight floor, wood, which I don't think you use in Indonesia. This is a medium weight floor in a structural steel building. And this is a heavy floor, which you will tend to use in Indonesia. Heavy precast flooring or heavy cast in situ flooring. So the floor will be heavy in your building. The live load in your building, it'll probably be office if it's a commercial building. What about your interior walls? Are they going to be light or heavy? I mean, I think you should try and make them lightweight to resist the earthquake force. And your exterior walls, let's say some of them are going to be bata merah, so say medium, and you're going to have a heavy roof. So now you're helping to work out the weight of your building. That's very important. Now we go to the floor plan. Let's say our building is going to be a rectangular, it's mainly going to be a rectangular building, say 40 meters by 20 meters, zoom to fit. Now your building is not going to be a boring rectangle. So you can change the shape of your floor plan by adding points to create a polygon. I mean, these points can go anywhere. And so like, this might be the shape of your building to suit your concept. You know, just for example, and here on this side, just a slight. So in Resist, you can have any shape of floor plan you want to. Any. And so you approximate your floor plan for your design in Resist so that Resist can calculate the correct weight of your building. This is the most important thing. So the floor area of your Resist model should be very close to the floor area of your design. Okay, so I'm just going to move these default structures to the perimeter of the building, just to move them out of the way. Now, yeah, so this is the plan. You will have lots of columns in your building just to resist the gravity loads. Columns and beams. Resist won't help you with that. You've got to go to another textbook to help you, like Ching, Illustrated Structures, to your gravity structure. Now, what about earthquake loads? You've got to put in the hazard factor. Well, you could just make a note that for Surabaya, the hazard factor is 0.3. And the soil type is, say, a medium soil. The softer the soil, the more structure you need. So that's the seismic factor, say, for Surabaya, the soil type. The next tab is the wind tab. And you don't need to worry about this in Indonesia because unless you're building a wooden building, then the wind forces are not critical. So you can forget about wind totally, okay? Just forget about it. Then we come to the structure in the X direction. So here's our building. In the X direction, this is the direction here. Well, at the moment, I've got 2 shear walls. That's the default option. But let's say we're going to have some moment frames in the X direction. So lateral structure in the X direction, I'm going to choose moment frames. What material? Well, let's assume reinforced concrete. And so the moment frames are going to look a bit like this. I mean, this is one of the buildings on my campus with perimeter moment frames. We can choose in our plan how many frames we want. I'm going to have 4 frames because that's going to suit my concept. See, I just right click and I choose, 1, 2, 3, 4. I'm going to remove this frame. I right click on it, delete. So you can see the 4 frames. At the moment, they're only 2 bays. So I'm going to add more bays. There, that'll do. I'm going to have 6 bays, and each bay length is 6 meters. So, you know, it looks like that. I'm going to just shift that frame inside the building. Oh, this frame here. It's going to be there. There we are. Okay, so I've got 4 frames, 6 bays long. Each bay is 6 meters. Notice that you as the designer, you can change this. Like we could make those bays just 4 meters long. This is to suit your concept and architectural program. But a 6 meter long beam is really sensible. The floor width supported by the beam. In other words, what width of flooring is supported by one of these beams? Well, let's just assume it's going to be about 8 meters. That means these beams are 8 meters apart. So that's okay. And then now I've got to just guess how big the columns have to be. Now, when I look at this building, these columns look pretty slender. So I'm going to make them a bit bigger. I'm going to make them about 60 centimeters there. Righto, now we go to the Y direction. Now in the Y direction, I'm going to use a structural core. So I'm going to use 2 shear walls. So I'm going to bring the shear walls in towards the center. Like that. And see, now I've got these 2 shear walls going up through the building. So in the lateral Y direction, I've got structural walls, reinforced concrete, 2 walls. Now I've got to guess the wall length. And I mean, these walls look too slender, so I'm going to make them like 6 meters long. And I'm going to make them, well, I'm going to try 20 centimeters thick. Okay, so now I have done my first design. I go to results. I click on the results tab. And I've got 2 graphs, results in the X direction, results in the Y direction. Now, if there's any red on these results, it means that my structure is too weak. Like for these moment frames, the shear forces in them are 71% of what the code allows. The bending moments in them are 114% of what the code allows. And the drift means the horizontal deflection during an earthquake. It's 140% of what the code allows. So my building is too flexible. I've got to increase either the number of structural elements or the size. So I'm going to just go back and increase the size of my columns and beams. My first guess was 0.6 meters, 0.65. There we are, 0.7 meters. There's no red here. And so my design is perfect in the X direction. I try and keep these figures close to 100% to make the structure as economical as possible. Let's look at these moment frames. Click on other results. The lateral separation in the X direction is 69% of the building width, which is okay. The width of the chosen column depth of my frame is 70 centimeters. Taking into account the reinforced concrete material I've chosen, the width of a column is 42 centimeters. Okay, so the columns are 70 by 42, and the beams, they are 70 by 36 centimeters wide. And this is information about the foundations, but you don't need to worry about that because that's under the ground, and I don't think you need to bother drawing that. What about in the Y direction? Well, the this is our reinforced concrete walls, remember, in the Y direction. We've got these two walls. That's what will resist the earthquake and nothing else. So we can see that I've got a real problem here. The drift is 270% of what the code allows. Failure. The shear force is okay. The bending moment is not okay either. But my building is far too flexible. In an earthquake, it's going to sway. It's going to vibrate far too far. So I go back to this tab, lateral structure Y, and I'm going to increase the wall length. There. These walls have to be 9 meters long. So that's what they look like. And what are the other results? The lateral structural separation for torsion is 26% of the building, well, length, which is acceptable. Penetrations, I'm only allowed very small penetrations in these walls because the walls are fully stressed. And this is information about the foundations. So this is also a very economical design. And now I have finished the design in this direction. Well, I finished the design in total. This is what you could use in your design if you wanted to. Let me just show you one thing. I told you how the walls have to be separated in plan to resist torsion. And you can see these walls are not separated by very much. Now, if I reduce that separation, I'm going to have problems. And so if I go back to my floor plan and I bring these walls closer, like that, see, I get the flashing light. And it tells me that I haven't got enough separation in plan. I'm going to have a problem with torsion. And so that's no good. That's not going to work. I'm forced to bringing those walls further apart. A bit more maybe. Let me just go back to the results. The software doesn't seem to be upgrading itself very well now, but you saw that previously this design worked. Now, say you say to yourself, or say to me, Andrew, I don't like this design because these walls are too long. Well, I'd say, well, okay, well, let's try 4 walls. So we go to the building plan and we put in 2 more walls. Say a wall there and a wall here. So you can see the 4 walls. Now we go to our results and we can reduce the amount of structure. I can reduce the wall lengths. And now the walls only need to be 7.5 meters long. This flashing light is turned into be a little bug. So we won't worry about that. But anyway, with 4 walls, the walls are only 7.5 meters long. And so this is what our final design looks like. And so now I've finished that design. If I'm happy with this design and I want to be able to show a tutor that I've done a safe design, I go to reports and I choose architectural report. But before I do that, I go to the 3D model and I adjust my model so that you can see the structure clearly. And I click on image and I click on set image for report. And this will be the image that gets printed out automatically with your 2-page architectural report. And so your 2-page architectural report will have that picture on it, and it will just have the percentages of those bar graphs, so you can prove that your numbers are less than 100%. And then there's just a summary of your input, so that you can prove to your tutor that you've modeled your building, you know, accurately enough. So that's pretty much all I want to say. Perhaps before leaving the software and inviting questions from you, I'll just show you a braced frame solution. So let's go to 3D model. Let's change our structural system in the Y direction. Let's use braced frames. And see, immediately we can see the braced frames there, replacing the shear wall. I'm going to use steel frames, and I'm going to use concentric frames. And I'm going to have 2 bays in each frame. And I'm going to make the bay lengths a bit shorter. I'll say about 5 meters. And I'm going to look at the results. Oh, the braces fail terribly because I need to make them bigger. There. And now that's what my structure will look like. And I finished my design. My braces are 35 centimeters by 35 centimeters in cross section. And now I've achieved a very safe design. If I go to results, the software tells me that my columns have to be 48 centimeters by 50 centimeters in dimension. And this is the depth of my beam in this design. So I think, one other thing before I finish, let's go back to this model again and say, look, I don't want to have 4 lines of moment frames. I just want 2 lines. So go back to my floor plan. I'm going to delete that frame. Well, let me delete this frame. So now this is my structure. 2 frames only in the X direction. I go to results. And actually, the frames are just on the limit. So that design is satisfactory because I'd slightly over-designed them before. But let's say I'm going to reduce the number of bays in the frame to say 3 bays per frame. So now my earthquake frames, I've just got 2 of them, and they're just there and there. And all the other columns of my building are going to be quite small because they just withstand the gravity forces. I go to results. Now, because I've only got 2 frames and I've only got 3 bays, the frames are failing. So I've got to make the columns quite a lot bigger. And I make them bigger. And there they are. They've got to be 1 meter deep. And so they look like that. They're quite large members, aren't they? Because after all, I've only got 2 frames and now I've only got 3 bays. So I'm just trying to show you how very quickly you can try out different ideas, try out different structural layouts and choose the layout, you know, that best suits your program and best suits your concept. And so now I'm going to stop sharing my screen and invite questions.
Oke, silahkan adik-adik yang akan bertanya tentang resist. Ada yang mau tanya? Silahkan raise hand. So, udah jelas belum penjelasannya tadi? Oke, Miranda. Silakan Miranda.
I want to ask about how we input our building shape to the resist. If we can do it.
Oh, I think you what you mean is if your building is not regular shape, right?
Yes.
Okay. Yeah. How?
Well, that's a good question. So I'll just share my screen again. You see, I have created an irregular shape here. So you go to your floor plan editor and you right click to add a point, and then you can just drag and you've got the dimensions shown here. So it's incredibly easy to create any shape you want to. I don't like that shape because it's got a bad re-entrant corner.
So the A is the dimension of the line?
Yes, I began by setting a rectangular plan, you know, where I put in the overall dimensions, and then I just made adjustments by dragging, I've gone back to rectangular. So, you know, I just have to add points and make it into an irregular delete element. Add points to make the building as irregular as you need to.
Andrew, the down part there in the display, you can find LX and then LY and A. Miranda is asking about the A. What is it about?
Or
The
A will be the area of your floor in square meters. So A is the floor area of my design.
So we can so we cannot input the the dimension that we want every line.
No, you can't. You
Okay.
can put in your I would suggest you start with your perimeter, a rectangular shape, and then you just modify it by adding in points, you know, and just dragging them.
Okay.
And the program would always tell you how many square meters per floor.
Okay, thank you, sir.
Yeah.
If the floors of your building change with the height, then I suggest you take an average floor area. That will be close enough.
That's the answer for the second question, Andrew. Actually, there is a student asking me privately about those questions. If they have a different area on each floor, then you have to input the average instead of like one by one, because it will be, the software calculates it.
Exactly. Just put in the average area and that will be close enough.
Yeah.
Remember, you don't want to try and be too accurate because this is rule of thumb design we are doing.
Yes, exactly. So, jadi adik-adik ya, ini kan rule of thumb. Jadi nggak usah detail-detail banget gitu kalau bikin apa namanya ukuran-ukurannya, yang mendekati aja gitu. Dan juga kalau bentuknya itu kayak misal kalian punya natural form atau yang kayak apa itu halus gitu, yang circular gitu dan nggak kotak-kotak gitu, anggap saja itu kotak-kotak gitu. Jadi itu akan mendekati bentuk yang ini. Semakin kalian bisa memahami bentuk dasar dari apa bangunan kalian, ini akan semakin mudah gitu, karena ini memang rule of thumb di mana kalian cuma mencari ini. Ini namanya preliminary design software ya. Jadi ketika kita mendesain di awal-awal itu kan nggak mungkin kita detail banget memasukkan segala sesuatunya. Kita hanya ingin mengetahui apakah konfigurasi seperti ini sudah benar atau tidak. Kalau sudah di preliminary design, terus kemudian kalian melanjutkan ke desain kalian, dikembangkan, barulah itu nanti urusannya civil engineer to calculate whether it fits or not gitu. Jadi this is only for the preliminary. So you don't have to be very detailed about your building, even the shape. So just follow the outline and then try to input this input your design into the software. Jadi kayak gitu. Ada lagi yang ingin bertanya?
Ibu Fenty, that was a very good summary. Thank you.
Yeah, because sometimes students are worried about what if it doesn't represent my design, but the thing is it's still preliminary design. We don't have to be like very detailed.
Exactly.
Yeah. Is there any questions regarding the software? Okay.
Answer one question. On the chat, a student is asking a question about if there are different heights between one floor and another floor. And if you have different heights, then once again, please take the average height. You know, this is quite a simplification, but just take the averages if you have, you know, changes of heights.
Okay. Is there any questions related to the software? or how to use it. If you don't have any question related to it, then I think there are still 2 questions from the previous session, Andrew.
Okay.
From Arya, he is asking that you have mentioned that shear walls are the best structural solution to earthquakes. How is that so? Is it best to make the structure as rigid as possible, or is it better to apply flexible joints in case the structure fails?
Yeah, well, if that's a really great question. The reason we can say shear walls are the best structural solution is because when we visit earthquake damaged regions, we always find that buildings with shear walls have suffered less damage. We also know that shear wall buildings are usually a lot stiffer and stronger than moment frame buildings. I mean, moment frame buildings are relatively flexible, and in an earthquake, they move a lot, and that causes a lot of damage. And so shear walls, because they are stiffer and stronger, are less prone to damage. And so as a rule of thumb, it is best, and it is indeed best, to make the structure as rigid as possible, because then it doesn't move as much and it doesn't cause as much damage to the non-structural elements like the partition walls, etc. And so it's really not a good idea to try and have flexible joints. That wouldn't be recommended. So yeah, that's a really great question. Well done.
Okay. Last questions we have. Oh, okay. If you have any more questions, you can write it down in the chat box or raise your hand. I will read the second questions in the chat box. From Alpha, I don't quite understand about one of design principle. Torsion resistance, separate parallel systems in plan. Can you explain it again? Do you mean that we don't have to bound parallel column, for example, in x-axis, using beam through other column, for example, in y-axis?
Okay, I'll try and explain this using my whiteboard. So let's take a square building and plan, a building square in plan. And during an earthquake, the building, due to the earthquake shaking, the building, is going to start sort of twisting. Now, to stop the twisting, to stop twisting, we need some structure in the y direction that is strong, so that when the building starts to twist, this structure, it will resist the twisting with a force like that. And this structure, it will resist the twisting with a force like that. And these two forces, they form a couple due to the separation between them. And so these forces multiplied by that distance gives an anti-torsional couple, which creates an opposite torsion force like that. And therefore it cancels out the torsion. And the same thing applies when we're considering torsion caused by the X direction. You know, we want some structure here and some structure here to resist the torsion in the same sort of way. So in this building, to stop torsion, one way would be to have a moment frame. These are columns. It's like 2 moment frames in the X direction, plus 2 moment frames in the Y direction. That will be more than enough to stop the torsion. And elsewhere in the plan, you'd have little columns just to resist the gravity loads, the weight of your building. That would be a really good structural solution. And of course, between these columns, you'd have beams supporting your floor slabs. And so, all your floor slabs create all your floors for your building. So I hope that is a bit clearer. How do you feel about that answer?
Yes, I think it's clear enough. It's very clear, Andrew. I think that's all for Andrew's lecture. I heard that you have another lecture after this. So I think if you need to ask about this lecture, you can ask me or Pak Iwan, and then we can ask Andrew if he has time to answer it, because we have a sort of tight schedule. So that's all for today. Thank you, Andrew, for your explanation. This is very clear, and I hope that students can apply this into their design.
Great. And can I just say one final comment?
Okay.
If you are interested in environmental resilience, the last disaster you want to avoid is your building collapsing in an earthquake, because then you're going to have to, that means you've lost all that embodied energy.
Exactly.
You're going to have to create a whole set of embodied energy for your new building. So the most environmentally resilient building is a building that is earthquake safe and won't collapse. Thank you, students. Thank you for your attention.
Okay, thank you, Andrew. Sekarang saya kembalikan ke Pak Iwan. Silakan, Pak Iwan.
Okay, thank you very much, Andrew, for your explanation. It's very clear. Terima kasih Bu Fenty sudah memandu pada hari ini. Waktu sudah menunjukkan pukul 09.58. Tentunya ini adalah akhir dari perkuliahan asas kita. Terima kasih kehadirannya untuk kelas A dan kelas B, kelas APA 3. Dan saya lihat tadi ada beberapa mahasiswa dari kelas PA2 dan yang lainnya. Terima kasih juga. Dan Bapak Ibu sekalian, Bu Windy dan Pak Irfan tadi yang telah bergabung, juga Bapak Ibu yang lain yang saya belum lihat, terima kasih. Semoga hari ini bisa memberikan inspirasi kita tentunya terkait dengan struktur ya. Jadi memikirkan kembali bagaimana struktur ini dalam fase preliminary design, sehingga Anda tahu bahwa shear wall sangat berguna untuk kita pikirkan untuk menjadi salah satu struktur yang konfigurasi struktur yang menyelamatkan kita tadi yang terkait dengan environmental resilience disampaikan oleh Pak Andrew barusan. Terima kasih. Oh ya, terakhir adalah untuk tugas resume, silahkan Anda submit sampai pukul 16.00 seperti biasa, seperti itu di classroom masing-masing. Terima kasih Bapak Ibu sekalian, Andrew for your kelas hari ini. Kelas akan kami tutup. Sampai berjumpa pada sesi APA 3 di hari Senin minggu depan. Dan jangan lupa minggu depan sudah presentasi tugas 2 seperti itu. Terima kasih. Kelas tutup. Selamat pagi. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
Waalaikumsalam.